Today we're going to be labeling the periodic table to represent electron configuration. Now, what is electron configuration? Well, really what's happening in electron configuration is that you're assigning an address to each electron in an atom for anything on the periodic table. Different elements have different atoms or numbers of electrons, and so depending on how many electrons each element has, they need to exist in a particular energy level, and so we want to represent that by something called electron configuration. Now there's a couple of rules that we need to follow. Electrons have to fill lower energy levels closer to the nucleus before they can start filling up higher energy levels. And so we're going to be assigning electrons closer to the nucleus first and then moving our way outward. Also, electrons are not going to share an orbital or an electron cloud, if you want to think of it that way, unless all the orbitals at that particular sublevel are occupied. So when an electron starts to fill an s orbital, it's kind of clear. There's only going to be 2 electrons in this orbital, so the first electron will fill it, and then the second electron just fills the same orbital. There's nothing special about the s orbitals. But when you're looking at the p orbitals, there are 3 p orbitals. They're all at the same energy level. And so an electron, the first electron that you add to the atom is going to fill the px orbital, which really means that the electron is going to exist in this energy level in this particular shape. And so if you think of it like an airplane who gives off, when you've looked up in the sky before and you see an airplane that gives off smoke behind it, you can follow the airplane's path because of that smoke path. Well, if you were able to follow the electron and its path for a period of time, it would develop this type of shape. So that's what's happening there. Well, then the next electron that you add also can stay in this energy level, and even though this can hold 2 electrons, they're not going to share one orbital when there's an available orbital. So the first electron will go into the px shape orbital, and then the next electron would go into py, and then the next electron would go into the pz orbital. Well, then when you start adding more electrons, well, since this can hold 2, that 4th electron, first, second, third, the 4th one will go back and share this orbital. Then the 5th one would go back and share this orbital, and the 6th electron would share this one. They're all in the same energy level, but they exist in different regions around the nucleus. Again, with the d orbitals, there are 5 different d orbital configurations, and so what will happen is when you are adding electrons at this particular energy level, they're going to do the same thing like they did with the p. There's 5 d orbitals at the same energy level, and the first electron will fill this orbital, and it will, again, if you followed its path like you would the smoke of an airplane, it would make a shape similar to this. Now, my drawings are very crude. If you actually look at the real drawings, s orbitals are shaped like a sphere, and they would look like this. P orbitals are along the x, y, and z axes, and then d orbitals look more like this. So what's happening is that first electron that's on this energy level would have this shape with its path. That's what the path would create. The second electron would have this shape and be in this location. The third electron, the 4th electron, and the 5th electron. Well, each of these orbitals can hold 2 electrons, and so the first 5 are all going to take each region so that they're by themselves. But then when you add the 6th electron, he's going to go back and share the space with this first one that you put in. And the 7th electron would share the space with the second one, and the 8th electron would share the space with the third one, and so forth. The maximum electrons in this particular energy level would be 10 electrons because there's 5 different shapes of the orbitals. Now, it looks kind of confusing, and I understand that. If we had the real Bohr model, what he thought, basically what would happen is you would add 2 electrons here, and then you would add 8 electrons here, and then you would add 18 electrons here, and it would be very simple. But unfortunately, in reality, the Bohr model is not correct. There's more of these shapes. You're going to add electrons to s orbitals, and then more s orbitals, and then p orbitals, and then you have more s orbitals. And so there's a certain sort of pattern to how these electrons are going to fill the orbital. So that's what we're going to do today. We're going to look at how the periodic table can help us demonstrate how these orbitals are filled. So the first thing we want to do is talk about all the s orbitals. And the s orbitals, or the s block, includes spheres, and that's the shape of the path. Excuse me. So what we're going to do is all of the s orbitals on the periodic table, we're going to color code with a red pen or pencil or marker or crayon or whatever you have. And I just want to point out that helium is actually being filled by an s orbital. It's way over here. And the reason it's over here with the noble gases is because it behaves that way, just like hydrogen is over here because it behaves more like your alkali metals. And so we have them in the position on the periodic table because of their behavior. But when we're talking about electron configuration, helium really should be positioned over here next to hydrogen. So the s orbital, the very, very first electron you add to an atom, which is the hydrogen atom, is going to be in an s orbital, which is a spherical shape. When you add another electron and proton to the atom, you're also going to be putting that second electron into that same spherical shape, and that's the path that it would follow. When you add a third electron and proton to an atom, it's going to go into a second s orbital. So there was a tiny s orbital on the inside. You can think of that as like a golf ball next to the nucleus or around the nucleus. And then the next one is going to be like a tennis ball size. So these s orbitals are concentric within each other. So the first two electrons are in the same s orbital, but then the next one is going to be in a new s orbital. Now these two electrons, the first electron would be lithium, and then if you add an electron and proton, it would be beryllium. These two are going to exist in the same s orbital also, because every single s orbital holds 2 electrons. If you were to add more electrons, they're actually going to fill up p orbitals, but let's ignore that for now. The next level of electrons that would go into an s orbital would be bigger, and it would be outside of this s orbital. So now you've got a golf ball inside of a tennis ball inside of a basketball. And then the next s orbitals would be even larger, and so outside of the tennis ball, would be a bowling ball, and then outside the bowling ball would maybe be a beach ball. And then the next s orbitals that you would fill would be even larger than that, and then larger than that. These are represent 2 electrons, and then even larger than that. So when you're adding or drawing your s orbitals, you want to draw them larger and larger and larger to represent that they're further away from the nucleus and they have more energy. The next type of orbital that we have are p orbitals, and we talked about that. The p orbitals have a dumbbell shape, and there's a px, a py, and a pz, which we talked about earlier, and you have it in your handouts. And what will happen is all of those p orbitals are going to exist in this block over here. And so we're going to use green to represent these orbitals. Now, the first p orbital, remember we talked about before, is the first electron is going to go on the x-axis, and then the next electron is going to actually be on the py axis, and then the third electron is going to be on the pz axis. So as you've added the electrons, excuse me, if you had 7 electrons in an atom, you can see that by the atomic number. The atomic number is the number of protons and electrons. So if you have 7 electrons in an atom, the first 2 electrons are going to go into that first s orbital. The second 2 electrons are going to go into the next bigger s orbital. And then the next 3 electrons will fill up some p orbitals, and these are your sublevels. Well, these can each hold 2, so I'm going to represent a px for that next 8th electron. It's going to go back and share this space with the first one. The next electron is going to share the space with the second, and the third electron is going to share the space with the pz. So as you're adding electrons and protons across the periodic table, you're assigning the electron a particular address or an orbital that it must occupy because of its energy level. So if you look again, we've already filled up 10 electrons. We can fill up 12 electrons by putting another S on the outside of that. Now we're going to start doing some P's again. So aluminum has 13 electrons. The first two have filled up the smaller S. The second two have filled up the larger S. The next 6 have filled up 3 of the P's. The next 2 have filled up an even larger S on the outside of that sphere. And then the last one has filled up a P by himself. Or actually, he hasn't filled it, he's just occupied it. So then we're going to continue with this pattern of assigning electrons to a particular orbital based on their energy level. And these represent px, py, and pz's, and then px, py, pz. This is the same px as this one, this is the same py as this one, and so forth. Now, if I were being more accurate, I would actually draw these larger and larger like I did the s's. It's just hard to get it all in the periodic table and be able to see what's happening when we draw it larger. But you can imagine that as you go down, they're larger and larger and larger p orbitals. Well, now we're going to move on to the d orbitals. The d orbitals, I like to say, are kind of like daisy-shaped. And the daisy-shaped orbitals we looked at before. There are 5 daisy-shaped orbitals, and so we're going to do the same thing like we did with the p. We're going to add each orbital in the order of energy. And so the first electron will be in the first orbital, and then the second orbital, and then the third, and then the fourth, and then the fifth. And then the next electron, the 6th electron, will come back and refill that first orbital. So we're going to do that in this area right here. It's called the d block because it has all the d orbitals in it, which kind of looks neat because it's similar to, this is why the periodic table is so nice. So this is the d block. Now the d block dropped. I say that it dropped once. It dropped one level because when I start assigning words or numbers to this, even though it's on the 4th energy level, it's actually 3D. So here we have the first d orbital, the second d orbital, the third d orbital, the 4th d orbital, and then there's that 5th one that kind of looks funny with the ring around the middle. And then again, the next electron that you add is going to be back at the first orbital. This one is going to share the space with the second one. This one will share the space with the third one, and this one will share the space with the 4th one. And this one, of course, will share the space with the 5th one down here. Okay, so if you filled the entire area with these shapes, it would be the same configuration. Now, finally, the F block is way down here at the bottom. I call F funky because the shapes are really kind of funky. They look sort of like complicated daisies, and you can look those up to see what those shapes look like. But the F block is down here, and I don't know if you've noticed, but it's always half of the amount of the block. If you notice over here, S has 2 electrons, can hold 2 electrons, and there's 2 blocks here. And it's one shape. Here, there's 1, 2, 3, 4, 5 shapes, and when you double 5, you get 10, which is the number of electrons, and this whole region right here holds 10 electrons perfectly. Similarly, down here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 14 electrons in this row, which means that there are 7 different shapes of the F block. So you have the first shape, the second shape, the third, the fourth, the fifth, the sixth, the 7th, and then this electron right here is going to share the region with the first one, and this one's going to share the region with the second one, and this one's going to share the region with the third one, and the 4th one, and the 5th one, and the 6th one, similarly like above. These 2 shared the same shape, these 2 shared the same shape, these 2 shared the same shape, and so forth. So it's that way. Now, finally, I want to point out before we stop is that the principal quantum number that we talked about earlier with the Bohr model is this number on the periodic table, and we're going to use that later. So this 1 is the lowest energy level, and that's the lowest quantum number. 2 is the next energy level, and that's the next quantum number. 3, 4, 5, and so forth. So as you're finishing up your periodic table, be sure it looks like this. Good luck.